This video will be a discussion of the chain fountain. In 2013, Steve Mould uploaded a YouTube video demonstrating what is now known as the Mould effect. In this demonstration, when allowing the beads to pour from a beaker, mysterious force causes the beads to jump above the beaker, pouring from above the starting position. To explain this, we will first look at the chains falling from a table and then from the chain fountain itself. While the chain fountain does show the presence of an additional force, a more observable approach is that of the chains falling from a table. Here we have two different orientations of beads. For one chain, the beads are organized together, while the other one has spacing in between each section of beads. For each organization, I will let the beads fall off the table. I will first play them one by one and then present a side-by-side comparison, where we will analyze the different movements of each chain. Here is the falling of the chain with a more spaced out organization. Notice that after being allowed to fall, the beads directly land next to the table. In addition, we see what looks like a pushback force where the back of the chain seems to travel backwards before being pulled off the table. This will be further explained. We'll now move on to the clumped together organization of the chain. What you may notice is that a pushback does occur, but the chain also travels away from the table. This is a very important change of behavior that needs to be analyzed further. We can now move on to a side-by-side comparison. The first point that should be made is that there is an additional force present other than friction and gravity. We know this by the pushing back behavior of the chain in both scenarios. The force of gravity is causing the chain to fall off the table, and friction can never cause an object to go backward, only resist the motion of an object. As a result, we know the force in question comes from the chain itself when experiencing a pull. Comparing the traveling of the chain, we find that the chain organized closer resulted in a greater distance traveled away from the table. With the close organization, the pushback force is exerted onto the row behind it, pushing the chain forward. This is an example of Newton's third law. The pushing back of the force when hitting an object such as the chain results in an equal and opposite reaction in the forward direction. With this force comes additional momentum, resulting in a faster initial horizontal speed when leaving the table. Given this idea of a change in momentum when pushing against an object, what would occur if the pushback motion of the chain was blocked by a wall? As you can see, the chain now has a block to push off against. The result of this is a greater distance from the table. Though it may not be clear to see, with the block, the chain traveled an additional 3 inches, traveling to the 9-inch mark of the ruler. For the movement without the block, the chain traveled 6 inches. This is the result of giving the chain a surface besides itself to push off against with the pushback force in question. With the concept of the backward force of the chain pushing off an object, we can now transition into the chain fountain. Instead of a wall and a horizontal orientation resulting in a forward increase in momentum, the chain fountain has a vertical orientation with the chain being contained in a beaker, with the force resulting in an increase in upward momentum. Here we have the beaker at 3 different heights, the table at 26.5 inches, a cabinet at 52 inches, and a shelf at 84 inches. In each scenario, I allow the beads to fall out the beaker. The pushback force described earlier results in the traveling of the chain higher than its starting position, directly on the beaker. When testing the chain fountain on the table at 26.5 inches, the chain hit a maximum height of 7 inches from the bottom of the beaker, averaging around the 6-inch mark. For the cabinet, at 52 inches, the peak generated reached the 11-inch mark of the meter stick. Finally, for the shelf, at 84 inches, the chain reached a peak of 15 inches from the bottom of the beaker. From these examples, the observed conclusion is that the Mould effect becomes greater when the starting height of the beaker increases. This behavior was also observed by researchers experimenting with the chain fountain. While we have proven that a force exists, we have yet to explain where the force comes from. It is believed that the force is a result of the restricted bending of the chain of beads. In any given scenario, a chain of beads will always have a fixed radius in order to turn. Here we have a picture of this condition. As you can see, the structure of the chain requires a certain amount of beads in order to complete a full circle. This is the reason why the Mould effect can only be repeated on chains instead of ropes. The movement of ropes is never restricted, and a rope can be manipulated by any means. This cannot occur with chains, as the compression of a chain is restricted. As a result, the rigidity of the chain when fully bent results in a unique force that cannot occur without a rope.